and he will build upon what Anshuman just shared, and then he'll conclude with a preview of what his thesis will be focusing on.
Thanks, Allegra.
You're welcome.
So, as said, this can be seen extent of Anshuman's work, where I try to make like a sidetrack and see the behavior of a structural on these samples. So, when we combine them with the seismic data and with the well data together with the Basin model results. So first, we all know that the first thing that we do when we receive a seismic image is try to establish a geological framework. And to do that, we need to put some geological expertise that we acquired visiting outcrops or in analogs. And we do that trying to interpreting stratigraphical surfaces and also faults. And then we have a present-day geological framework to build upon our computations in Basin modeling. And remember that when we do that, we are just making a simplification of what we've seen on the seismic image. But as we use a seismic image, we must be careful because seismic images are built upon velocity models. And even though you can have like velocity models that looks pretty similar over here, if you change some properties on velocity models, you can also change your seismic image. And this is just an example showing that pretty similar velocity models with minimal velocity changes can also change your interpretation of some surfaces, as you can see over here. And but in the other hand, we can see that different velocity images also can have pretty similar seismic images. And this is built upon the non-uniqueness that we have when we are building a velocity model on seismic during seismic processing. That velocity models that are pretty smooth, and other velocity models that has some constraints on geological features, such as different lithologies, they can build the same data. It's here shown on this graph that the M axis is related to the model, that is the velocity model, and the D axis is the seismic data. So even though you have totally different models, they can almost recover the same data. And this is shown here on a pre-salt Santos Basin that here, considering a smooth salt velocity, we have this seismic image, but when we consider salt with different lithologies, we can have the same, almost the same seismic image, even with some enhancements and improvements on below the salt. So we're gonna build upon that we can try to sample from the other velocity models that unfortunately we not are able to find them during a seismic processing. So a way that we can try to do it is try to incorporate geological processes on the velocity and then see if these velocities from incorporated geological processes can recover the seismic data. And that's what all Anshuman said on the previous presentation. So the workflow performs as an integrated tool where we use our knowledge on geological basin modeling to get some results on pore pressure and porosity and even in mineral volume fractions. And with these results, where before in the basin modeling you have some input parameters, Then we have these results. With these results, we go to the rock physics modeling, the other discipline that we will build our velocity models. And then with these velocity models, we can go to the model that is the wave kinematics and see if the seismic data and the velocity that you built upon all our geological process can recover the data that you have. And then when you go through all the cycle, we can have like the posteriors, is like you start with the priors and then you have the posteriors and try to make a structural uncertainty on them. So here I try to put all this workflow in a Bayesian view in an equation, and showing that all these vector called B are all your Bayesian model input parameters. And you can treat some of them like a static or others like uncertain. So after you go with this B model, B vector, you can create your Bayesian model and then have your results that I'm gonna call H. And with these results H, we go to our velocity model through the rocks physical modeling. Then you have your velocity that you go to another discipline to see if the velocity goes with your wave propagation model and see if the seismic matches it. So during each step, we can calibrate it to well data when we go to the results of Bayesian modeling, and then when you have the velocity, you can calibrate it to seismic data. And after all this calibration, you're gonna have your posteriors that are the parameters that are able to back with the data that you have. So as shown by Anshuman, I'm gonna use the same location to do the studies for the structural uncertainty, where we only use like 51 uncertainty parameters. That is the 10 layers here with 5 parameters changing for each layer and 1 universal parameter that was the heat flow shown by Anshuman. And we're gonna see the impact of them in the structural behavior of the interfaces of your geological framework. So, but to you to have the structural geological framework, you need the velocity, and what we do is a rock physics modeling that we grab all the results from the priors from your Bayesian modeling, and you put it together in a rock physics modeling with some assumptions, and then you can create your velocity model. And why we need this results from the Bayesian model? Because the velocity is pressure sensitive. Then we need all the total pressure and the pore pressure to create the effective pressure and perform the computations to recover the velocity from these geological processes. And now I'm going like sidetracks on the Anshuman's workflow, and I only gonna grab now the velocity from these Bayesian modeling results and compute the behavior of our structural framework. Then we take our original framework, we pass through the legacy velocity model that was used to create the seismic image, where we interpreted this original framework, and we go to the time domain. And then after we, in this time domain, we take the new velocity realization and back to depth domain and to check what's the difference between them on positioning. But as Anshuman said, we are dealing with distributions, and we have to sample from priors. And as we sample, make a lot of sample, a lot of realizations, we're gonna have like a bunch of new structural models. So to try to analyze them, we need to go to use some statistical tools. And one of them is performing a PCA on all your geological framework results. So you can get eigenvectors that can reflect most of the samples. And this is what I'm trying to represent here is the two most important eigenvectors from all the samples that we can have. So this is, you have to think this is like a vector that each sample can be projected on this and see how much weight that sample has on each eigenvector. And doing that, we can try to analyze the variability on these samples. And the two eigenvectors that are shown the previous slide, they represent almost 80% of your samples. Then only seeing these two axes, we can see the variability that we have on our geological framework. And from the priors, before any calibration, we can see that we have a nice spread of possible geological frameworks. But when, and this point here is our original framework where all the Basin models were computed. But when we try to calibrate, when we do a calibration on well, we can see that we can shrink our variability and see that, okay, your Basin models can recover the well data, they at least have to be over here, your new structural models from that velocity. And then when we constrain with the seismic data, we see that, oh, it's not so, it's not like a big cloud. You have to be more near to your original framework. And this is like a nice interpretation because we don't expect to the geological framework to change a lot. So when you have your priors and you condition to all the data that you have, that is the well data and the seismic data, you can see that our your geological framework also does not have to change a lot, but it changes a little bit. So with this data, we can try to perform structural uncertainty. And here is like a summary of the structural uncertainty. That this is like the positioning of our section in Z and X, and the colors represent the interfaces probability to be happen. And one thing that we notice is that when we are in the deep part, we have a few variability. So it's like, okay, you have you are more certain where your layer on the shallow part is gonna be. But at the deep parts, your variability tends to increase. This is like a result you should expect. And here on the black, I'm just underlining our original framework that all the Basin models came from. We can see kind of a little mismatch, but this can be explained by one thing that we didn't consider our structural framework also as like uncertain. And that's why we need to do another iteration, because as we're gonna have now new geological frameworks, we also can consider these new geological frameworks as uncertainty. So that in that B parameter that I only put like uncertain, the 51 parameters, now I'm gonna have another new parameter as uncertain. That is gonna be my structural framework as uncertain. And so to wrap up all the steps that we did over here, what we are trying to do is to extract the information from seismic data and the well logs together with the geological processes. So to do that, we started with this workflow to quantify uncertainty related to all Basin modeling parameters. And I try here to incorporate the structural uncertainty as an extension of this workflow as we compute the velocities. And with that, we can assess Basin modelings in an interdisciplinary approach, also including geological framework differences. So with that, we can verify our velocity models together with interpretations and see if they are compatible or not. And depends on your assumptions. If you think that okay, but my original interpretation was not so good, you can think then now your interpretation as also like a uncertainty parameter. And also you can think in another way. Okay, I have to revisit all my model assumptions and see if they are okay. And they are matching with my interpretations. So one way to do that is trying to make another iteration, revisiting your interpretation and your assumptions with this workflow again. So it's like an iterative workflow. And this work that I did was all thinking about other steps that I want to try to use this workflow in more complex geological process, such as the abnormal pressure generation areas with complex geology. And I want to try to start with the models that can account with all possible kinds of abnormal pressure generation, and then construct their results to check with the well data and the seismic data, and see the certainty of pore pressure when we try to include faults and other kinds of abnormal pressure generation. So here is the next steps of my undergoing studies, that is consider like the geological framework as also an uncertain parameter, and try to apply this workflow in another geological area. And also include when faults are presented, I want to try to include them as uncertainty too. And this is trying to be wrapped up and try to be put on the Northern Viking Graben on my future works. And I want to thank all the industrial affiliates of BPSM to support us and making us doing this great works. And any questions on you can send to Allegra on the chat. Thank you.
Thanks, Josue. I'd like to share a couple of questions and comments that came in after Anshuman spoke, but I know they're relevant to you too, so I just want to share them with the group. And so those comments were, what tool are you using? Let's see, what tool are you using for the Bayesian modeling? Was it Netica API? And then Tapan responded, the tool for Bayesian modeling is a combination of MATLAB, Python codes, along with Petramod. And Anshuman responded, we use MATLAB. As Allegra mentioned, we have a MATLAB toolbox that integrates with Petramod. Parameterization of uncertainty and Monte Carlo sampling is done in MATLAB. And then for every sample, we run that in MATLAB, and codes are available on GitHub. And that's one of the things I was discussing in the part of my introduction regarding adding value, which is that we have shared this workflow on our GitHub site. One comment was that this was great work on Schumann, and we can't wait to hear Josue close the loop. And then there is one new message below. I use MATLAB. This is Tanvi speaking. I use MATLAB for running the simulations in Petramod, Python to collect the simulation outputs, just because she's more comfortable with Python. And for Bayesian network and influence diagram computation, she used a software which I'm actually going to copy paste into our tiny URL. And I will put the tiny URL back in the bottom of the chat. You'd have to scroll way up to see it. So with that, any other questions? We will go to Anatoly. And I'd like to just make an editorial comment, which is that both Josue and Anatoly have an important thought partner in Ebba Hartz at Aker BP. Okay, Anatoly?
Yeah, right, yeah.